This is Group 3. Introducing Thomas, Luke, Jordan, and Savas. This presentation is on structural and geotechnical finite element analysis. The AutoCAD file was imported into Strand 7. The nodes were joined together to create the element. The AutoCAD file was imported into Strand 7 a second time to get the node position for the cafe. The steel cantilever structure and cafe were later transposed onto each other. The location of the slanted columns was measured in AutoCAD, was typed into the Create Node box. The connection between the beams and the columns is pinned connection. The connection of the column to the foundation is a rigid connection. The blueprint of the structure was color-coded to keep track of the member schedule. It can be checked by using group. The principal axis of the rafters had to be rotated 90 degrees. The rafters were offset by 225 millimeters. Members can only withstand a certain amount of elongation before they fail. Linear analysis requires only input of Young's modulus and Poisson's ratio. The software assumes the material only has elastic deformation. The design engineer needs to check the maximum deflections and stresses if any members will fail.
Using finite element analysis, a design check was conducted into the Jacaranda Square walkway located in Sydney Olympic Park. The structure was modelled using Strand 7 to produce a set of results, allowing the structurally imposed loads were verified with additional calculated data using the processes outlined in AS4100. The main column axial force produced a result of 262.91 kilonewtons, which is verified by the result of 835.5 kilonewtons. The strut axial force produced a result of 124.18 kilonewtons, which is verified by the result of 316.0 kilonewtons. The cable axial force produced a result of 0.42 kilonewtons, which is verified by the result of 70.7 kilonewtons. The tire column axial force in compression produced a result of 37.24 kilonewtons, which is verified by the result of 43.3 kilonewtons. The tire column axial force in tension produced a result of 36.5 kilonewtons, which is verified by the result of 230.9 kilonewtons. The deflection serviceability of the structure was verified compared to the maximum allowed deflection outlined in AS4100, using the equation delta is less than or equal to the span over 125. The deflection of the structure's cantilever was gathered from the model's results. The cantilever, which measured a maximum deflection of 7.54 millimeters occurring at the cantilever end, was below the allowed deflection of 46.87 millimeters. Based on the gathered results, it can be concluded that the Strand 7 model is an accurate representation of the structure. All Strand 7 outputted results were able to be verified with the corresponding AS4100 values. As a result, the Jacaranda Square walkway structure is deemed to comply with the relevant Australian standards.
Hi, my name is Jordan and I'm going to talk about the formation of the strip foundation model for the Geoproject. There were two options for the model, that being the strip foundation on the ground, and the other option was the strip footing that was embedded into the ground, which was the one that we picked. We ended up going through about 4 models all up. The first took quite a while to run, and so we ended up changing that out, or redoing that model, just fixing up the gradients in here. That model, once we were trying to run it to get results, we realized that it wasn't converging. So because of that, we ended up trying to go back to the first option. When we did that, that model also wasn't converging. So we made a model with as simple geometry as we could, and that model was also not converging. We realized that it was a problem with the material properties, and we used that model to try and find that problem. Once we found that problem, we ended up moving back to that second model that we made with good geometry, and it's shown here. The problem that we ended up finding in the material properties was that our cohesion was entered in wrong. As you can see here, we put it in as 50, and that's in pascals. It's actually meant to be 50 kilopascals or 50,000. Yeah, so that was because of incorrect units there. Because of this, the model wasn't converging and it was taking really long to run. I think that's because it was just making really big deflections in other areas in the model, and so because of that, the model wasn't actually getting a chance to converge properly, and so yeah, that was making it take a really long time to run. Once we did end up fixing that, the model ran faster and it converged, obviously, so we moved that change to the rest of the models and we ended up getting some good results. I'm going to pass them over to Luke and he'll talk about those results.
Using strand 7, our group produced numerous graphs describing how the soil behaves under loading. These graphs included load settlement curves for the basin shaft, displacement vectors for the soil underneath footing, vertical and horizontal settlement graphs, and stresses of the soil underneath the footing. Our group also produced other graphs displaying the effects of increasing the cement in the foundation. The mean effective stress increment and volumetric strain increment curves, as well as the shear stress increment and shear strain increment curves were displayed. These were made into collaborative graphs for better visualization. Using this information gathered from strand 7, our group was also able to plot load and settlement curves using Excel. The bearing capacity in kilonewtons per meter was plotted against the displacement. The formula PU equals P of the base plus P of the shaft is used to calculate the final bearing capacities. The bearing capacities for each value of percentage of cement were calculated and are shown in the table below. To verify these results, Skempton's method was used as a traditional method for verification. The formula above describes the method we went about to calculate those bearing capacities. Some notable trends the group noticed while increasing the percentage of cement in the foundation. The bearing capacity of the soil improved with the increase of cementation. Peak forces in load settlement curves decreased while increasing the cement. Maximum stresses in stress diagrams decreased. Displacement values were lessened. It also noted that it is predicted using strand 7 software that any further increase in cementation will result in the foundation becoming brittle and too stiff to carry sufficient loading. Overall, across the two projects, our team found strand 7 effective for the purposes of finite element analysis for both structural and geotechnical projects. We find strand 7 will be beneficial for real-world model predictions for future projects. Thank you for listening.